The universe is vast, mysterious, and full of secrets that even the brightest minds in astrophysics struggle to explain. We've mapped distant galaxies, peered into the hearts of black holes, and even detected ripples in space-time itself. And yet, despite all our advancements, there are cosmic anomalies that defy our understanding, leaving scientists scratching their heads and sparking debates that stretch the boundaries of what we know. These aren't just small mysteries, they're profound questions that challenge the very foundations of modern science. From dark energy's relentless push to the strange behavior of rogue planets, these anomalies remind us just how much we still have to learn. In this video, we're diving into 22 of these cosmic puzzles phenomena that continue to baffle researchers and ignite our curiosity about the universe's deepest mysteries. So, are you ready to explore the enigmatic corners of space that keep astrophysicists up at night? Let's begin. Imagine a universe where most of the matter is invisible, shaping galaxies, bending light, and holding entire cosmic structures together, yet completely undetectable by any instrument we've ever built. This isn't science fiction, this is dark matter. It makes up roughly 27% of the universe, dwarfing the amount of ordinary matter that forms stars, planets, and even us. But here's the catch: we've never seen it, touched it, or directly observed it in any way. So how do we know it's there? The answer lies in gravity. Galaxies spin faster than they should if only the visible matter were holding them together. Light from distant objects bends in ways that can't be explained without something massive, yet invisible, exerting its pull. One of the most striking pieces of evidence comes from the Bullet Cluster, where two galaxy clusters collided. The visible matter slowed down, but something unseen kept moving, dragging the gravitational effects with it. That something is dark matter, but what is it made of? Scientists have spent decades searching for particles that could explain it, from weakly interacting massive particles to actions. Yet despite countless experiments deep underground and in space, dark matter continues to elude us. It's as if the universe is playing a cosmic game of hide and seek, and we're still searching for the rules. Could it be a new kind of particle? Or is it something even stranger, something beyond our current understanding of physics? And as we grapple with this invisible enigma, another mysterious force looms in the background, equally invisible and even more perplexing: dark energy. But that's a story for the next anomaly. If dark matter is the universe's ghostly skeleton, then dark energy is its shadowy puppeteer, an invisible force that's pulling the strings of the cosmos in ways we can barely comprehend. While dark matter holds galaxies together, dark energy is doing the opposite. It's pushing the universe apart, driving its expansion faster and faster. This discovery came as a shock to astronomers in the late 1990s when they observed distant supernovae. These exploding stars appeared dimmer than expected, suggesting the universe wasn't just expanding, it was accelerating. This finding upended decades of scientific consensus and pointed to something even stranger than dark matter: a mysterious energy permeating space itself. Today, we know dark energy makes up about 68% of the universe, far more than dark matter or ordinary matter. But what is it? One leading idea is the cosmological constant, a concept first proposed by Einstein. It suggests that empty space isn't truly empty. It's filled with a constant energy density that exerts a repulsive force. But here's the problem. When physicists calculate how much energy this constant should have, their predictions are off by an astonishing factor of 1 followed by 120 zeros. That's not a small discrepancy, it's one of the biggest mismatches in the history of science. The implications are staggering. If dark energy continues to dominate, the universe will keep expanding at an ever-increasing rate, eventually tearing apart galaxies, stars, and even atoms in a distant future event called the Big Rip. But what if dark energy isn't constant? What if it changes over time or interacts with other forces in ways we don't yet understand? These questions cut to the heart of modern physics, challenging our understanding of gravity, space-time, and the very fabric of reality. As we grapple with this cosmic conundrum, it's worth remembering that not all mysteries are found in the distant reaches of space. Some are much closer to home, hidden in the familiar yet enigmatic objects that populate our own solar system. And that brings us to the next anomaly, the strange, wandering worlds known as rogue planets. Now, imagine a force so powerful it's pulling entire galaxies, including our own Milky Way, toward it at incredible speeds. This isn't the plot of a sci-fi movie, it's the Great Attractor, one of the most puzzling gravitational anomalies in the universe. Located about 250 million light-years away in the direction of the constellations Centaurus and Hydra, this mysterious region exerts an immense gravitational pull, drawing galaxies toward it at speeds of over 600 kilometers per second. But what exactly is it? The Great Attractor lies in a region of the sky known as the Zone of Avoidance, an area obscured by the dense dust and gas of the Milky Way's disk. This makes it incredibly difficult to study, as the very material that makes up our galaxy blocks our view. For decades, astronomers could only infer its existence by observing the strange motion of galaxies being tugged toward it. It wasn't until the advent of infrared and X-ray telescopes that we began to peer through the veil and catch glimpses of what lies beyond. What we've discovered is astonishing. The Great Attractor isn't just a single object, it's part of a much larger cosmic structure known as the Laniakea supercluster, a vast web of galaxies spanning over 500 million light-years. Within this supercluster, the Great Attractor acts as a gravitational focal point, pulling galaxies into its orbit. But even this explanation raises more questions than answers. What could possibly be dense enough to exert such a pull? Some theories suggest it's a massive concentration of dark matter, while others propose it's the result of countless galaxies clustering together in a way we don't yet fully understand. The challenges of mapping this cosmic structure are immense. Not only do we have to contend with the Milky Way's dust, but we also have to piece together the motions of galaxies across vast distances. It's like trying to map a city by only seeing the shadows of its buildings. Yet, despite these hurdles, each new discovery brings us closer to unraveling the mystery of the Great Attractor. As we continue to explore this enigmatic region, it's a reminder that the universe is filled with large-scale structures that defy our expectations. From superclusters to cosmic voids, these formations reveal a cosmos far more complex and interconnected than we ever imagined. And just as the Great Attractor pulls galaxies toward it, it pulls us deeper into the mysteries of the universe, mysteries that challenge our understanding and inspire us to keep searching for answers. Speaking of large-scale structures, the universe has even more surprises in store, from colossal walls of galaxies to vast, empty voids. But that's a story for another anomaly. Beyond the icy reaches of Pluto lies a cosmic boundary that has left astronomers baffled, a sharp, unexpected drop-off in the number of objects in the Kuiper belt known as the Kuiper Cliff. This region, which extends billions of kilometers from the Sun, is home to countless icy bodies, remnants from the early days of our solar system. Scientists expected the number of these objects to gradually decrease the farther out you go. But instead, at a distance of about 50 astronomical units, that's 50 times the distance between Earth and the Sun, the population of Kuiper belt objects suddenly plummets. It's as if someone drew a line in the cosmic sand and said, "No further." So, what could explain this abrupt boundary? one intriguing possibility is the existence of a hidden planet lurking in the outer solar system, sometimes referred to as Planet 9. This hypothetical world, thought to be several times the mass of Earth, could have gravitationally swept the area clean, pushing objects inward or ejecting them entirely. Another theory suggests that gravitational interactions with passing stars or disturbances from the Milky Way's tidal forces might have disrupted the outer Kuiper belt, scattering its objects into the void. To unravel this mystery, scientists turn to the New Horizons mission, which famously flew by Pluto in 2015 and has since ventured deeper into the Kuiper belt. By studying the composition and distribution of objects in this distant region, New Horizons has provided invaluable data, offering clues about the solar system's formation and evolution. Yet, despite these efforts, the Kuiper Cliff remains a puzzle, a stark reminder that even our own cosmic backyard holds secrets we're only beginning to uncover. The Kuiper Cliff isn't just a scientific curiosity, it's a window into the early solar system, a time when planets were still forming and the gravitational dance of celestial bodies shaped the structure we see today. Solving this mystery could shed light on how planetary systems evolve, not just here but across the galaxy. As we ponder the mysteries of the Kuiper Cliff, it's worth remembering that our solar system is full of other unexplained phenomena, from the strange orbits of distant objects to the enigmatic forces shaping planetary landscapes. And as we venture further into the cosmos, we find that each discovery raises new questions, drawing us deeper into the wonders of the universe. Speaking of wonders, let's turn our attention to another cosmic anomaly, one that challenges our understanding of planetary formation and the delicate balance of forces that govern the cosmos. In the vast expanse of space, even the smallest anomalies can reveal profound truths about the universe. Take the Pioneer 10 and 11 spacecraft, for example. These trailblazers of the outer solar system, launched in the early 1970s, were designed to explore Jupiter, Saturn, and beyond. But as they ventured farther from Earth, something strange happened. They began to slow down in a way that defied the laws of physics as we know them. This unexpected deceleration, now known as the Pioneer Anomaly, became one of the most intriguing mysteries in space exploration. For decades, scientists meticulously analyzed the spacecraft's trajectories, only to find that both Pioneer 10 and 11 were experiencing a tiny but consistent force pulling them back toward the Sun. This force was too small to be explained by gravity alone. It was as if some unseen hand was gently tugging on the spacecraft. Theories began to emerge, ranging from the mundane to the extraordinary. One idea suggested that thermal radiation, emitted unevenly from the spacecraft's power systems, could be pushing them slightly off course. Another, more radical possibility was that this anomaly hinted at new physics, perhaps a modification to Einstein's theory of relativity or the influence of dark matter in ways we don't yet understand. The implications of the Pioneer Anomaly are significant. If it's caused by something as simple as thermal radiation, it could help engineers design more precise spacecraft for future missions. But if it points to new physics, it could revolutionize our understanding of gravity, space, and time itself. While recent studies have leaned toward the thermal explanation, the debate isn't entirely settled. The Pioneer Anomaly reminds us that even well-understood phenomena can hold surprises, and that the universe often challenges us to think beyond the limits of our current knowledge. As we reflect on the mysteries of these pioneering spacecraft, it's worth noting that they're not alone in their journey. Other missions like Voyager 1 and 2 have also encountered unexpected behaviors as they venture into interstellar space. These anomalies remind us that the farther we go, the more questions we uncover, questions that push the boundaries of science and inspire us to keep exploring. And speaking of exploration, our next anomaly takes us even deeper into the cosmos, where a strange and powerful signal from deep space has left astronomers both puzzled and intrigued. In the vast silence of space, where countless stars whisper their faint radio signals across the cosmos, one sound stood out so starkly that it earned an exclamation point in its name: the wow. Signal, detected on August 15, 1977, by the Big Ear radio telescope at Ohio State University. This brief but powerful burst of radio waves lasted a mere 72 seconds, yet it remains one of the most tantalizing mysteries in the search for extraterrestrial intelligence. The signal was so extraordinary that astronomer Ray Anomaly, who first spotted the data, circled it on the printout and wrote "wow" next to it. The signal's intensity was off the charts, reaching 30 times the background noise and matching the expected signature of a transmission from an intelligent source. It came from the direction of the constellation Sagittarius, but there was no known star, planet, or natural phenomenon in that region capable of producing such a signal. What made the WOW signal so intriguing was its narrow frequency band, centered around 1,420 MHz, a frequency range often associated with hydrogen, the most abundant element in the universe. This led to speculation that it could have been a deliberate beacon designed to catch the attention of anyone listening. Yet, despite numerous attempts to detect it again, the signal has never been heard since. The mystery of the WOW signal has fueled decades of debate. Some scientists argue it could have been a natural phenomenon, like a comet or a passing asteroid reflecting solar radiation. Others believe it might have been a fleeting sign of extraterrestrial intelligence, a brief hello from a civilization far beyond our reach. The challenge, however, lies in the fleeting nature of the signal itself. Without a repeat detection, it's nearly impossible to confirm its origin or even study it further. This enigmatic event underscores the difficulties of searching for signals in the vastness of space. Radio telescopes must sift through an ocean of cosmic noise, from pulsars to quasars, in hopes of finding a needle of potential intelligence. And while the WOW signal remains a tantalizing clue, it's far from the only unexplained transmission we've encountered. From fast radio bursts to other anomalous signals, the cosmos seems to be full of whispers we're only beginning to hear. As we continue to listen to the stars, each unexplained signal reminds us of the boundless mysteries that lie beyond our understanding. And just as the WOW signal challenges us to consider the possibility of life beyond Earth, another cosmic anomaly invites us to explore the strange and violent phenomena that shape the universe. Let's turn our attention to the next mystery: gamma-ray bursts, the most energetic explosions in the cosmos. Gamma-ray bursts may be the most explosive events in the universe, but they're not the only fleeting cosmic phenomena that leave scientists scrambling for answers. Enter fast radio bursts, or FRB, intense, millisecond-long flashes of radio waves that originate from galaxies billions of light-years away. These bursts pack an extraordinary amount of energy, equivalent to what the Sun emits over several decades, all compressed into a fraction of a second. First discovered in 2007, FRBs have since become one of the most enigmatic puzzles in modern astrophysics. The mystery begins with their sheer unpredictability. Most FRBs occur just once, vanishing as quickly as they appear, leaving astronomers with little more than a blip of data to analyze. A few, however, have been observed repeating, offering tantalizing clues about their origins. One of the most famous repeating FRBs, known as FRB 1211, has been traced to a small, star-forming galaxy 3 billion light-years away. But what could possibly produce such powerful, fleeting signals? Theories abound, ranging from the exotic to the speculative. Some scientists believe FRBs are linked to highly magnetized neutron stars called magnetars, whose intense magnetic fields could generate these bursts during starquakes or flares. Others suggest they might result from collisions between neutron stars or black holes, releasing immense energy in the process. And then there's the more provocative idea: could FRBs be signals from advanced extraterrestrial civilizations, beacons sent across the cosmos to communicate or power interstellar spacecraft? While this possibility captures the imagination, most researchers lean toward natural explanations, though the truth remains elusive. To unravel the mystery, scientists have turned to cutting-edge telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. Located in British Columbia, CHIME is uniquely designed to scan large swaths of the sky for radio signals, making it an ideal tool for detecting FRBs. Since its commissioning in 2017, CHIME has discovered hundreds of these bursts, mapping their locations and studying their properties in unprecedented detail. Each detection brings us closer to understanding what causes these cosmic flashes, but the puzzle is far from solved. What makes FRBs so fascinating isn't just their mystery, it's what they reveal about the universe. As these radio waves travel across vast distances, they interact with the diffuse gas between galaxies, allowing scientists to measure the distribution of matter in the cosmos. In a way, FRBs are like cosmic messengers, carrying information about the large-scale structure of the universe itself. As we continue to probe these fleeting signals, it's clear that the universe is full of transient events that challenge our understanding. From gamma-ray bursts to fast radio bursts, these phenomena remind us that the cosmos is alive with activity, much of it fleeting, mysterious, and profoundly powerful. And just as FRBs hint at the dynamic nature of the universe, another anomaly takes us even deeper into the heart of cosmic chaos: the enigmatic behavior of black holes. Black holes are among the most extreme and mysterious objects in the universe, warping space-time and defying our understanding of physics. But even they have their quirks, and one of the strangest is the phenomenon of black hole spin. Some black holes rotate at incredible speeds, approaching the theoretical limit set by the laws of physics. This rapid spinning creates a whirlpool of space-time around the black hole, dragging everything nearby, even light, into its frenzied orbit. But here's the puzzling part: not all black holes spin at the same rate. Some are sluggish, barely rotating at all, while others are cosmic speed demons. What determines how fast a black hole spins? The answer likely lies in its formation and the way it consumes matter over time. Yet, this raises another question. Could the spin of a black hole reveal clues about its history or even the universe itself? The study of black hole spin is more than just an academic curiosity. It has profound implications for our understanding of gravity, space-time, and the evolution of galaxies. For instance, rapidly spinning black holes can launch powerful jets of particles and radiation, shaping their surroundings and influencing star formation across vast distances. These jets are some of the most energetic phenomena in the universe, and their origins are still not fully understood. As we delve deeper into the mysteries of black holes, it's clear that these cosmic enigmas are far more dynamic and complex than we once thought. From their formation to their role in shaping the universe, black holes continue to challenge our assumptions and push the boundaries of science. And just as we grapple with the secrets of these gravitational giants, another profound question arises, one that touches on the very nature of life itself. Now let's turn to a cosmic mystery that bridges the gap between astrophysics and philosophy: the Fermi Paradox. Named after physicist Enrico Fermi, this paradox highlights a striking contradiction. Given the vastness of the universe and the high probability of life-sustaining planets, why haven't we found any evidence of extraterrestrial civilizations? The math suggests there should be billions of potentially habitable worlds, and countless civilizations advanced enough to communicate across the stars. Yet the silence is deafening. One explanation is the concept of the Great Filter, a hypothetical barrier that prevents life from reaching an advanced stage. This filter could occur at any point in the development of civilizations, from the emergence of life itself to the ability to colonize other planets. If the filter lies in our past, humanity might be extraordinarily lucky to have made it this far. But if it lies ahead, the future could be far more uncertain, with existential threats looming on the horizon. Another possibility is that interstellar communication is far more challenging than we imagine. The vast distances between stars, the limitations of light speed, and the sheer timescales involved could make it nearly impossible for civilizations to connect. Or perhaps advanced civilizations choose to remain hidden, avoiding detection for reasons we can't yet comprehend. The Fermi Paradox forces us to confront fundamental questions about our place in the cosmos. Are we truly alone, or is the universe teeming with life that we simply haven't found yet? As we search for answers, technologies like the James Webb Space Telescope and initiatives like SETI are expanding our ability to explore these possibilities. Yet the paradox remains unresolved, a reminder of how much we still have to learn about the universe and our place within it. And as we ponder the silence of the cosmos, another cosmic anomaly beckons, one that challenges our understanding of the very fabric of reality. Let's explore the mystery of dark flow, a phenomenon that suggests the universe might be far stranger than we ever imagined. Now, let's turn our attention to a cosmic oddity so strange that it's been given a name straight out of a science fiction thriller, the axis of evil. This mysterious alignment in the cosmic microwave background radiation, or CMB, has left scientists scratching their heads and questioning some of the most fundamental ideas about the universe. The CMB is often called the afterglow of the Big Bang, a faint, ancient light that fills the cosmos, carrying clues about the universe's infancy. But within this relic of the early universe lies something unexpected, a peculiar pattern that seems to defy the principles of randomness we'd expect from the Big Bang. The axis of evil refers to an alignment of temperature fluctuations in the CMB that appear to follow a specific direction across the sky. These fluctuations, which represent tiny variations in density and temperature from the early universe, should be random and evenly distributed if the Big Bang unfolded as we think it did. Instead, researchers have found that these fluctuations show a strange coherence, as if the universe has a preferred axis, a cosmic line along which these patterns align. So, what does this mean? For one, it challenges the cosmological principle, a cornerstone of modern physics that states the universe should look the same in all directions on large scales. If the axis of evil is real, it suggests that the early universe may not have been as uniform as we've assumed. This has profound implications for our understanding of the Big Bang and the forces that shape the cosmos. Could this alignment hint at something beyond our current models, like an unseen influence from a neighboring universe or a flaw in our theories of inflation, the rapid expansion that followed the Big Bang? The search for answers has led scientists to scrutinize the CMB with ever greater precision. Missions like the Planck satellite have mapped the CMB in extraordinary detail, revealing subtle patterns and anomalies that continue to puzzle researchers. Some have suggested that the axis of evil could be a statistical fluke, a trick of the data rather than a real feature of the universe. Others argue that it points to new physics, perhaps a fundamental asymmetry in the early universe that we've yet to uncover. As the debate continues, the axis of evil serves as a reminder that even our most well-tested theories can be upended by unexpected discoveries. It's a humbling thought. The universe, as vast and complex as it is, still holds secrets that challenge our understanding of its origins. But the mysteries of the early universe don't end with the axis of evil. beyond this enigmatic alignment lies another anomaly, one that takes us even further back in time to the very first moments after the Big Bang. Let's explore the next puzzle, the Horizon Problem, a cosmic conundrum that questions how the universe became so uniform in the first place. The Hubble constant, a number that tells us how fast the universe is expanding, has been at the heart of cosmology for over a century. It's a cornerstone of our understanding of the cosmos, yet it's also the source of one of the most perplexing anomalies in modern astrophysics, the Hubble tension. This tension arises from a glaring discrepancy in how we measure the universe's expansion rate. Depending on the method used, scientists arrive at two different values for the Hubble constant, and they don't agree. Here's the problem. When we measure the expansion rate using nearby objects like Cepheid variable stars or supernova, we get one number. But when we look at the cosmic microwave background radiation, the faint afterglow of the Big Bang, we get a different, slightly lower number. The difference might seem small, a matter of just a few kilometers per second per megaparsec, but in the precise world of cosmology, it's a huge deal. It's like trying to measure the height of a building and getting two different answers depending on whether you use a ruler or a laser. So, what's causing this tension? One possibility is that there's an error in our measurements. Maybe we've underestimated the distance to nearby stars or misjudged the brightness of supernova. But after decades of refining these techniques, the discrepancy persists, suggesting something deeper might be at play. Another explanation is that our understanding of the universe is incomplete. Perhaps there's an unknown ingredient or force influencing the expansion rate, something that wasn't accounted for in our models. The implications are profound. If the Hubble tension points to new physics, it could reshape our understanding of dark energy, dark matter, or even the fundamental laws governing the cosmos. Imagine discovering that the universe isn't expanding as we thought. It could open up entirely new avenues of research, challenging everything from the age of the universe to the fate of galaxies. As astronomers continue to refine their measurements and explore new methods, the Hubble tension serves as a reminder that even the most fundamental questions in science can still hold surprises. It's a puzzle that pushes us to think bigger, dig deeper, and question what we think we know. And while the Hubble tension captures much of the attention, it's not the only unresolved issue in astrophysics. From the nature of dark matter to the behavior of black holes, the universe is full of mysteries that challenge our understanding. Each one invites us to keep exploring, to keep questioning, and to keep uncovering the secrets of the cosmos. Speaking of mysteries, our next anomaly takes us deeper into the heart of the universe, where another cosmic puzzle awaits. Let's delve into the strange and elusive phenomenon of fast radio bursts, a mystery that's as fleeting as it is powerful. Picture this: the universe is made up of atoms, the building blocks of everything we see, stars, planets, even you and me. This ordinary matter, known as baryonic matter, should account for about 5% of the universe's total content. But here's the catch: when scientists tally up all the visible matter they can observe, a significant portion seems to be missing. This is the missing baryon problem, a cosmic puzzle that has left astrophysicists scratching their heads for decades. So, where did all this matter go? The answer might lie in the cosmic web, a vast network of filaments made up of gas and dark matter that stretches across the universe. These filaments connect galaxies and galaxy clusters, forming the backbone of the cosmos. Hidden within these threads is a reservoir of hot, diffuse gas, so faint and spread out that it's nearly invisible to traditional telescopes. This intergalactic gas, often referred to as the warm-hot intergalactic medium, or WIM, could hold the key to solving the missing baryon mystery. Detecting this elusive gas is no easy task. It doesn't emit much light, and its temperature makes it difficult to observe directly. To track it down, scientists have turned to indirect methods, like studying how the gas absorbs light from distant quasars, extremely bright objects powered by supermassive black holes. By analyzing these absorption patterns, researchers can piece together the distribution and properties of the WIM, slowly filling in the gaps of the cosmic inventory. Recent advancements in technology have brought us closer to solving this mystery. X-ray telescopes like the Chandra Observatory and ultraviolet instruments, such as those on the Hubble Space Telescope, have provided glimpses of the WIM in action. Simulations of the cosmic web have also helped refine our understanding, showing how baryonic matter flows through the universe's largest structures. Yet, despite these breakthroughs, the missing baryons remain elusive, a testament to how much we still have to learn about the cosmos. The implications of this anomaly are profound. If we can account for the missing baryons, it would not only solve a long-standing mystery, but also provide crucial insights into the formation and evolution of galaxies. It's a reminder that even the most familiar components of the universe can hold surprises, challenging us to look deeper and think differently. As we grapple with the missing baryon problem, it's worth noting that this isn't the only cosmic inventory discrepancy we've encountered. The universe is full of missing pieces, from dark matter to dark energy, each one hinting at a larger, more complex picture waiting to be uncovered. And speaking of missing pieces, our next anomaly takes us into the realm of the invisible, where another cosmic enigma awaits: the nature of dark matter. Now, let's dive into one of the most mind-bending puzzles in modern physics, the black hole information paradox. At its core, this anomaly pits two of the most successful theories in science against each other: quantum mechanics and general relativity. Quantum mechanics tells us that information about the universe, like the properties of particles, can never be truly destroyed. But general relativity, which describes the behavior of black holes, suggests that when matter falls into a black hole, it's gone forever, taking its information with it. So what happens to that information? Is it lost, or is it somehow preserved? This is the heart of the paradox, a question that has stumped physicists for decades. The debate gained momentum in the 1970s when Stephen Hawking proposed that black holes aren't completely black. Instead, they emit a faint glow of radiation, now known as Hawking radiation. This radiation, Hawking argued, would slowly cause black holes to evaporate over time, eventually disappearing entirely. But here's the catch: Hawking radiation is random, carrying no information about the matter that fell into the black hole. If the black hole evaporates completely, what happens to all that information? Does it just vanish, violating the laws of quantum mechanics? Or is it somehow encoded in the radiation, hidden in a way we can't yet detect? For years, this paradox seemed unsolvable, but in recent decades, breakthroughs in string theory and quantum gravity have offered new perspectives. One leading idea is the holographic principle, which suggests that all the information about the matter swallowed by a black hole is stored on its surface, encoded in tiny, two-dimensional bits. When the black hole evaporates, this information could be released back into the universe, preserved in the form of Hawking radiation. Another intriguing proposal is the concept of firewalls, hypothetical walls of energy at the edge of a black hole that could destroy incoming matter but somehow preserve its information. The implications of solving this paradox are enormous. It could reconcile quantum mechanics and general relativity, two theories that have long resisted unification. It might also reshape our understanding of space, time, and the very nature of reality. But the mystery is far from solved. Even as new theories emerge, the black hole information paradox continues to challenge our most fundamental ideas about the universe. As we grapple with this cosmic conundrum, it's worth noting that black holes are full of other mysteries waiting to be unraveled. From their event horizons to the singularities at their cores, these gravitational giants hold secrets that could redefine our understanding of physics. And while the information paradox may be one of the most profound, it's just the beginning of what black holes have to teach us. One such mystery lies in the strange and elusive nature of black hole singularities, points where the laws of physics as we know them break down completely. But that's a story for another anomaly. Deep within the constellation Eridanus, far beyond the reach of even the most powerful telescopes, lies a cosmic emptiness so vast it defies comprehension. This is the Eridanus Supervoid, a region of space stretching over 1 billion light-years where galaxies are almost entirely absent. To put that into perspective, if our Milky Way were dropped into this void, its nearest galactic neighbor would be hundreds of millions of light-years away, a lonely existence in an otherwise crowded universe. The Eridanus Supervoid isn't just a curiosity, it's a puzzle that challenges our understanding of the cosmos. What makes it even more intriguing is its potential connection to the cold spot, a mysterious patch in the cosmic microwave background radiation, or CMB. This cold spot, first spotted by the Wilkinson Microwave Anisotropy Probe, is a region of the universe that's slightly cooler than its surroundings. At first glance, this might not sound significant, but in the context of the Big Bang, even a tiny temperature variation can hint at something extraordinary. Scientists have long speculated that the cold spot could be a shadow cast by the Eridanus Supervoid. The idea is that as light from the CMB travels through the void, it loses energy, a phenomenon known as the integrated Sachs-Wolf effect. This energy loss could explain why the cold spot appears cooler. But here's the twist: the sheer size of the Eridanus Supervoid makes it an anomaly in itself. According to our current understanding of cosmology, such a massive void shouldn't exist. The universe's large-scale structure is thought to be relatively uniform, with matter distributed in a cosmic web of filaments and nodes. A void this large pushes the boundaries of that model, raising questions about how it formed and what it means for our understanding of the cosmos. Some theories suggest that the Eridanus Supervoid could be the result of a rare fluctuation in the early universe, a statistical outlier in the otherwise smooth distribution of matter. Others propose more exotic explanations, such as the influence of another universe beyond our own, a concept tied to the idea of a multiverse. While these ideas remain speculative, they highlight just how little we know about the true nature of the universe's large-scale structure. The Eridanus Supervoid isn't just a scientific curiosity, it's a window into the universe's deepest mysteries. Its existence challenges our assumptions, forcing us to rethink the rules that govern the cosmos. And as we continue to explore these vast, empty regions, we're reminded that the universe is full of surprises, from the tiniest particles to the largest structures. Speaking of large-scale structures, our next anomaly takes us even further into the cosmic web, where another mysterious formation awaits: the Great Wall, a colossal assembly of galaxies that stretches across the universe like a cosmic spine. But that's a story for the next anomaly. In October 2017, astronomers spotted something extraordinary, a visitor from beyond our solar system. This enigmatic object, named Oumuamua, meaning scout or messenger in Hawaiian, became the first confirmed interstellar object ever observed passing through our cosmic neighborhood. But Oumuamua wasn't just a milestone in astronomy, it was a mystery wrapped in a riddle. At first glance, Oumuamua appeared to be a typical asteroid or comet, but its behavior quickly set it apart. For starters, its shape was unlike anything we'd ever seen. A long, cigar-like object stretching hundreds of meters in length, but only a fraction as wide. This peculiar form was so unusual that it defied the typical round or irregular shapes of most known space rocks. But the real head-scratcher came when scientists noticed something even stranger. Oumuamua was accelerating. Objects moving through space typically follow predictable paths dictated by gravity, but Oumuamua seemed to be speeding up on its own, as if propelled by an unseen force. This unexpected acceleration sparked a flurry of theories. Some suggested it might be a comet with outgassing material acting as a natural thruster. But unlike comets, Oumuamua showed no visible tail or coma, the cloud of gas and dust that usually accompanies such activity. Others proposed more radical ideas, including the possibility that Oumuamua was an artificial object, perhaps a piece of alien technology like a solar sail or spacecraft designed to harness sunlight for propulsion. The debate over Oumuamua's origin and nature remains unresolved, in part because the object was gone almost as quickly as it arrived. By the time it was detected, Oumuamua was already on its way out of the solar system, leaving astronomers with only a brief window to study it. This fleeting glimpse made it nearly impossible to gather definitive data, leaving scientists to piece together clues from limited observations. Despite the challenges, Oumuamua has opened a new chapter in our exploration of the cosmos. It's a reminder that interstellar space is full of objects we've yet to discover, each one potentially holding clues about the origins of stars, planets, and even life itself. Since Oumuamua's discovery, other interstellar visitors like the comet Borisov have been detected, hinting that such objects may be more common than we once thought. As we continue to scan the skies for these cosmic wanderers, Oumuamua remains a symbol of the universe's endless capacity to surprise us. Whether it's a natural oddity or something more extraordinary, it challenges us to think beyond the boundaries of our solar system and imagine what else might be out there waiting to be discovered. And as we ponder the mysteries of interstellar visitors, another cosmic anomaly invites us to look even deeper into the strange and fleeting flashes of energy that light up the universe. Let's turn our attention to the next enigma, fast radio bursts. At the heart of our galaxy lies a cosmic beacon, a dense and bustling region of stars, gas, and dust. But hidden within this luminous core is a mystery that has puzzled scientists for years, an unexplained flood of gamma-ray radiation. Known as the galactic center excess, this strange signal doesn't match any known source of gamma rays, leaving astronomers to wonder what could be producing such intense energy. The Milky Way center is home to a supermassive black hole, countless stars, and a chaotic dance of cosmic activity. Naturally, you'd expect some gamma rays here. These high-energy photons are often produced by violent events like supernova or the interactions of cosmic rays with gas clouds. But when scientists measured the gamma-ray emissions, they found far more than could be explained by these familiar processes. The excess radiation forms a diffuse glow, concentrated around the galactic center, and its origin remains one of the most tantalizing puzzles in astrophysics. So, what could be causing this mysterious glow? One leading theory points to dark matter, the elusive substance that makes up most of the universe's mass. If dark matter particles collide and annihilate each other, they could produce gamma rays as a byproduct. This idea has sparked excitement among researchers, as it offers a potential way to detect dark matter indirectly. However, not everyone is convinced. Some argue that the excess could come from a population of pulsars extremely dense, rapidly spinning neutron stars that emit powerful beams of radiation. These pulsars, which are difficult to detect individually, might collectively produce the observed gamma-ray signal. The debate has led to a surge in research, with scientists analyzing data from telescopes like NASA's Fermi Gamma-Ray Space Telescope to uncover clues. By mapping the distribution and energy of the gamma rays, they hope to determine whether the signal aligns more closely with dark matter or pulsars. The challenge lies in distinguishing between the two, as both scenarios can produce similar patterns. It's a bit like trying to identify a distant orchestra by its sound. You might hear the music, but picking out individual instruments is much harder. The galactic center excess isn't just a scientific curiosity. It's a window into the fundamental forces shaping our galaxy. Whether it's a sign of dark matter or a swarm of pulsars, solving this mystery could reveal new insights into the nature of the universe. And as we continue to probe the heart of the Milky Way, we're reminded that even our own galactic backyard holds secrets waiting to be uncovered. But the mysteries of our galaxy don't end at its core. Beyond the gamma-ray glow, there are other enigmas lurking in the vast expanse of space, phenomena that challenge our understanding of the cosmos itself. Let's turn our attention to one such anomaly, the perplexing behavior of rogue planets, worlds adrift in the void without a star to call home. Among the many puzzles the universe has handed us, one of the most perplexing lies not in the vastness of space, but in the very building blocks of matter itself. This is the Lithium Problem, a discrepancy that strikes at the heart of our understanding of the Big Bang and the formation of the elements. According to the theory of Big Bang nucleosynthesis, the early universe should have produced specific amounts of light elements, hydrogen, helium, and a trace of lithium, as it cooled and expanded in its first few minutes. While hydrogen and helium match predictions almost perfectly, lithium is a different story. Observations show that there's only about 1/3 as much lithium in the universe as the models say there should be. So, where did all the lithium go? This question has stumped scientists for decades. One possibility is that our understanding of nuclear physics during the Big Bang is incomplete. Perhaps reactions involving lithium were more complex than we thought, or maybe unknown processes destroyed lithium shortly after it formed. Another intriguing idea is that lithium could have been absorbed or transformed over billions of years by stars, effectively hiding it from our observations. But even this explanation has its challenges, as stars are known to produce lithium in some cases, not just destroy it. The lithium problem isn't just a minor hiccup in cosmology. It's a fundamental challenge to our understanding of the universe's earliest moments. If the predictions of Big Bang nucleosynthesis are off, even by a little, it could mean that our models of the early universe need significant revision. This would have ripple effects across astrophysics, potentially altering our understanding of everything from the formation of galaxies to the behavior of dark matter. To tackle this mystery, scientists are exploring multiple avenues. Some are refining their calculations of nuclear reactions in the early universe, while others are searching for clues in the atmospheres of ancient stars, which preserve the chemical fingerprints of the cosmos's infancy. Meanwhile, laboratory experiments are probing the properties of lithium and its isotopes, hoping to uncover new insights into how it behaves under extreme conditions. The lithium problem reminds us that even the smallest elements can hold the keys to the universe's biggest questions. It's a humbling thought. Something as simple as a missing trace of lithium could force us to rethink the very origins of everything we see around us. And while lithium may be the most famous elemental mystery, it's far from the only one. The universe is full of chemical enigmas, from the uneven distribution of heavy elements to the strange behavior of rare isotopes. Each one offers a tantalizing glimpse into the processes that shape the cosmos, and the secrets that still lie hidden within it. Speaking of hidden secrets, our next anomaly takes us into the realm of the bizarre, where the very fabric of reality seems to twist and warp in ways we can barely comprehend. Let's explore the mystery of cosmic strings, hypothetical threads of energy that could stretch across the universe, shaping its structure in ways we're only beginning to understand. Imagine a rain of particles streaming down from space, each one carrying unimaginable energy, some so powerful they rival the force of a fastball pitch, but packed into a single subatomic speck. These are cosmic rays, high-energy particles that bombard Earth from all directions, and while they've been studied for over a century, they still hold a puzzling secret. Their energy distribution doesn't match what our theories predict. This is the cosmic ray anomaly, a mystery that challenges our understanding of the universe's most energetic events. Cosmic rays are thought to originate from some of the most violent phenomena in the cosmos: supernova explosions, the collisions of neutron stars, and the jets of active galactic nuclei. When a star explodes as a supernova, it sends shock waves rippling through space, accelerating particles to nearly the speed of light. These particles, mostly protons and atomic nuclei, then travel across the universe, some eventually reaching Earth. But here's the puzzle. When scientists measure the energy of these cosmic rays, they find that there are far more high-energy particles than our models of supernova and other sources can explain. Studying these particles is no easy task. Cosmic rays don't travel in straight lines. They're deflected by magnetic fields as they journey through space, making it nearly impossible to trace them back to their origins. To make matters more complicated, by the time they reach Earth, they've often interacted with the atmosphere, creating a cascade of secondary particles that must be carefully analyzed to reconstruct their original energy and composition. The implications of this anomaly are profound. If our understanding of cosmic ray sources is incomplete, it could mean there are other, even more powerful processes at work in the universe, processes we haven't yet discovered. Some theories suggest that ultra-high-energy cosmic rays might come from exotic objects like gamma-ray bursts or even the decay of hypothetical particles left over from the Big Bang. Others propose that our models of particle acceleration in supernova need a major overhaul. Whatever the explanation, the cosmic ray anomaly reminds us that the universe is full of surprises, even in the most fundamental processes we think we understand. It's a humbling reminder that, for all our advancements, there's still so much we don't know about the forces shaping the cosmos. But cosmic rays aren't the only particle mysteries waiting to be unraveled. From neutrinos that barely interact with matter to antiparticles that seem to defy expectations, the subatomic world is full of enigmas that challenge our understanding of physics. And as we explore these mysteries, we're reminded that the universe's secrets aren't just written in the stars, they are also hidden in the tiniest particles that fill the void. Speaking of particles, our next anomaly takes us even deeper into the subatomic realm, where a strange imbalance in the universe's fundamental building blocks has left scientists searching for answers. Let's delve into the mystery of matter-antimatter asymmetry, a puzzle that could hold the key to why the universe exists at all. Tucked away in the constellation Monoceros, about 2,300 light-years from Earth, lies a cosmic gem that defies the typical chaos of the universe. Known as the Red Rectangle Nebula, this striking structure is one of the most visually stunning and scientifically puzzling objects in the night sky. Unlike the swirling, chaotic shapes of most nebulae, the red rectangle boasts an almost perfect geometric symmetry, with its namesake rectangular shape and a lattice-like pattern of glowing, intersecting lines. It's as if the cosmos decided to paint a masterpiece, blending art and science in a way that leaves astronomers both awestruck and baffled. The red rectangle's unique appearance is thought to be the result of a binary star system at its core. These two stars, locked in a tight orbital dance, are surrounded by a thick disk of dust and gas. As material from the stars spills outward, it's funneled into the shape of two cones, creating the nebula's distinctive X-like structure. The precise alignment of these cones, combined with the way light scatters off the dust particles, gives the red rectangle its vibrant red hue and intricate patterns. But while this explanation accounts for the nebula's basic form, the details remain shrouded in mystery. How did the dust and gas arrange themselves so perfectly? And why does this nebula look so different from others we've observed? Studying the red rectangle is no easy task. Its distance and the complexity of its structure make it a challenging target for even the most advanced telescopes. Observations in infrared light have provided some insights, revealing the presence of complex organic molecules like polycyclic aromatic hydrocarbons, or PAR, which are thought to play a role in the nebula's red glow. These molecules, often found in regions of star formation, are some of the building blocks of life, adding another layer of intrigue to the red rectangle story. Could this nebula hold clues about the chemical processes that lead to the emergence of life? Binary star systems like the one at the heart of the red rectangle are not uncommon, but they rarely produce such striking nebulae. This raises questions about the specific conditions that gave rise to this cosmic oddity. Is it the result of a rare stellar interaction, or is there something unique about the way these stars are evolving? The answers could shed light on the broader processes that shape planetary nebulae, the glowing remnants of dying stars that populate our galaxy. As we marvel at the red rectangle's beauty, it's a reminder that the universe is full of surprises, even in the most familiar cosmic phenomena. From its geometric perfection to the mysteries of its formation, this nebula challenges us to rethink what we know about the life cycles of stars and the intricate interplay of forces that shape the cosmos. But the red rectangle is just one of many enigmatic nebulae that captivate astronomers. From the haunting beauty of the ghost of Jupiter to the cosmic fireworks of the Crab Nebula, these celestial structures continue to reveal the universe's boundless creativity and its endless capacity to surprise us. And as we turn our gaze to the next anomaly, we'll explore another cosmic wonder that pushes the boundaries of our understanding even further. Now, let's turn our attention to a star that has captured the imagination of both scientists and the public alike, Tabby Star. Officially known as KIC 8462852, this enigmatic star lies about 1,400 light-years away in the constellation Cygnus. What makes Tabby Star so fascinating is its bizarre and unpredictable dimming behavior. Unlike most stars, which dim in regular, predictable patterns caused by orbiting planets, Tabby Star flickers and fades in irregular, dramatic dips, sometimes losing up to 22% of its brightness. This strange behavior has sparked a whirlwind of theories, from the scientific to the speculative, making it one of the most talked about cosmic mysteries of our time. When astronomers first noticed these unusual dimming patterns in data from NASA's Kepler Space Telescope, they were baffled. The dips were too large and irregular to be explained by typical planetary transits or stellar activity. One of the most tantalizing and controversial theories proposed that the star might be surrounded by an alien megastructure like a Dyson sphere designed to harness its energy. While this idea captured headlines and imaginations, most scientists remain skeptical, pointing out that natural explanations are far more likely. So, what could be causing these dramatic dimming events? One leading hypothesis is that Tabby Star is surrounded by a massive cloud of dust and debris, possibly the remnants of a shattered planet or comet swarm. As these fragments orbit the star, they could occasionally block its light, creating the irregular dips we observe. Another possibility is that the star itself is undergoing unusual magnetic activity, causing it to dim in unexpected ways. Yet, despite years of observation and analysis, no single explanation has fully accounted for all the star's peculiar behavior. Studying Tabby Star hasn't been easy. Its irregular dimming makes it difficult to predict when and where to look, requiring constant monitoring. This is where citizen science has played a crucial role. Through projects like Planet Hunters, amateur astronomers from around the world have helped sift through vast amounts of data, identifying patterns and anomalies that might otherwise go unnoticed. Their contributions have been invaluable, highlighting the power of collaboration in solving some of the universe's most perplexing puzzles. As researchers continue to study Tabby Star, they're not just unraveling the mystery of one star, they're learning more about the diverse and often unpredictable nature of stellar systems. Every new observation brings us closer to understanding what's really happening around this cosmic oddity, whether it's a swarm of comets, a dust cloud, or something even more extraordinary. Tabby Star is a reminder that the universe is full of surprises, even in the most seemingly ordinary places. And while the idea of alien megastructures might be a stretch, the search for answers continues to push the boundaries of our knowledge. But Tabby Star isn't the only stellar anomaly that's left scientists scratching their heads. From hypervelocity stars racing across the galaxy to binary systems with bizarre orbital dances, the cosmos is full of stars that defy expectations. And as we explore these stellar oddities, we're reminded that the universe is far stranger and more wonderful than we ever imagined. Now, let's shift our gaze to another cosmic enigma, one that takes us beyond the realm of stars and deep into the mysteries of spacetime itself. Now, let's explore one of the most astonishing and eerie regions of the universe, a place where galaxies are almost entirely absent, and the vastness of space feels almost empty. This is the Boötes Void, a cosmic desert so immense that it defies imagination. Spanning over 330 million light-years, it's one of the largest known voids in the universe. To put that into perspective, if you place the Milky Way at one end, it would take light traveling at its incredible speed, over 300 million years to reach the other side. And yet, within this unimaginably vast expanse, there are only a handful of galaxies, scattered like lonely islands in an endless ocean. The Boötes Void, named after the constellation in which it's located, was discovered in the 1980s during a survey of the universe's large-scale structure. At first, astronomers were stunned by its sheer emptiness. Voids are a normal part of the cosmic web, the intricate network of filaments and clusters that make up the universe, but the Boötes Void is exceptional. It's not just a gap, it's a chasm, a region so devoid of matter that it challenges our understanding of how the universe organizes itself. So, how did such a massive void form? One theory suggests that it's the result of smaller voids merging over billions of years, creating a supervoid. Another idea is that it's a relic of the early universe, a region where matter was less dense compared to its surroundings. As the universe expanded, this underdense region grew into the colossal void we see today. But even these explanations leave questions unanswered. Why is the Boötes Void so much larger than other voids? And what does its existence tell us about the forces that shape the cosmos? Studying the Boötes Void is no small feat. Its sheer size makes it difficult to map, and its sparse population of galaxies offers few clues about its origins. To make matters more complicated, the void's emptiness means there's little light to observe, leaving astronomers to piece together its structure from faint signals and indirect measurements. Yet, despite these challenges, the Boötes Void has become a focal point for research, offering a unique window into the universe's large-scale structure and the forces that govern it. The implications of this void are profound. Its existence challenges the cosmological principle, the idea that the universe should look roughly the same in all directions on large scales. If voids like Boötes are more common than we think, it could mean that the universe is far more uneven and complex than our current models suggest. This could reshape our understanding of dark energy, dark matter, and even the Big Bang itself. As we ponder the mysteries of the Boötes Void, it's worth noting that it's not alone in the cosmos. Other voids, like the Eridanus Supervoid and the Local Void, also dot the universe, each one offering its own set of questions and challenges. These cosmic deserts remind us that the universe is full of extremes, from the densest clusters of galaxies to the emptiest stretches of space. And as we turn our gaze to the next anomaly, we'll explore another cosmic extreme, one that's not about emptiness but about energy. Let's dive into the mystery of quasars, the brightest and most energetic objects in the universe. Among the smallest and most elusive particles in the universe lies a mystery that has puzzled physicists for decades: the neutrino anomaly. Neutrinos, often called ghost particles, are nearly massless, electrically neutral, and so weakly interacting that they can pass through entire planets without leaving a trace. Yet, despite their elusive nature, neutrinos have a surprising habit of shape-shifting, or oscillating, between three different types: electron, muon, and tau neutrinos. This phenomenon alone was groundbreaking when first discovered, proving that neutrinos have mass and challenging the standard model of particle physics. But there's a catch. The way neutrinos oscillate doesn't always add up, creating a discrepancy known as the neutrino anomaly. The crux of the anomaly lies in the mismatch between theoretical predictions and experimental observations. When scientists calculate how neutrinos should oscillate based on known physics, their predictions don't fully align with what's actually measured in experiments. For example, some experiments detect fewer electron neutrinos than expected, while others observe unexpected patterns in neutrino behavior. These inconsistencies suggest that something is missing from our understanding, perhaps a fourth type of neutrino, known as a sterile neutrino, that doesn't interact with matter at all and only affects oscillations. Alternatively, the anomaly might point to flaws in our current models of neutrino behavior, or even hints of new physics beyond the standard model. Detecting neutrinos is no easy task. These particles are so faint that scientists rely on massive, highly sensitive detectors buried deep underground to shield them from other cosmic noise. Facilities like the Ice Cube Neutrino Observatory in Antarctica, the Super Kamiok and in Japan, and the Deep Underground Neutrino Experiment in the United States are at the forefront of this research. These experiments use everything from giant tanks of ultra-pure water to vast arrays of sensors embedded in ice to capture the fleeting interactions of neutrinos. Yet, even with these advanced tools, the neutrino anomaly remains stubbornly unresolved, a testament to how challenging these ghostly particles are to study. The implications of solving this anomaly are enormous. If sterile neutrinos exist, it would revolutionize our understanding of particle physics, potentially opening the door to new theories about the nature of matter and the universe. It could also shed light on dark matter, as some theories suggest that sterile neutrinos might be a component of this mysterious substance. On the other hand, if the anomaly stems from flaws in our current models, it could lead to a deeper rethinking of the standard model itself, one of the most successful frameworks in science. As researchers continue to probe the mysteries of neutrinos, they're not just chasing a single anomaly, they're exploring the very edges of our knowledge. Every new experiment brings us closer to understanding these enigmatic particles and the role they play in the cosmos. While the neutrino anomaly captivates physicists, it's far from the only particle puzzle waiting to be solved. From the strange behavior of quarks to the search for new forces of nature, the subatomic world is full of mysteries that challenge our understanding of reality. And as we turn to the final anomaly, we'll explore one of the most profound questions in physics. Why does the universe contain more matter than antimatter? This imbalance, known as matter-antimatter asymmetry, is a mystery that could hold the key to why everything from galaxies to stars to life itself exists at all. The universe is a tapestry of light and shadow, heat and cold, but one patch of this cosmic fabric stands out as particularly puzzling. In the vast expanse of the cosmic microwave background radiation, The faint afterglow of the Big Bang, there's a mysterious cold spot, a region significantly cooler than its surroundings. This anomaly, first detected by the Wilkinson Microwave Anisotropy Probe, has sparked intense debate among scientists. What could cause such a stark temperature variation in the ancient light of the universe? The cold spot is no small blip on the cosmic radar, spanning a region of the sky large enough to hold thousands of galaxies. It's one of the most significant deviations from the otherwise smooth and uniform CMB. At first glance, it might seem like a statistical fluke, a rare but natural fluctuation in the early universe. However, the odds of such a large cold region appearing by chance are incredibly slim. So slim, in fact, that some researchers argue it points to something far more profound. One leading theory connects the cold spot to the Eridanus Supervoid, a vast, nearly empty region of space stretching over 1 billion light-years. The idea is that as light from the CMB travels through this void, it loses energy due to a phenomenon called the integrated Sachs-Wolf effect. This energy loss could explain why the cold spot appears cooler. But here's the twist: the Eridanus Supervoid itself is an anomaly. According to our current understanding of cosmology, voids this large shouldn't exist. The universe's large-scale structure is thought to be relatively uniform, with matter distributed in a web-like pattern of filaments and nodes. A void of this size pushes the boundaries of that model, raising questions about how it formed and what it means for our understanding of the cosmos. Some scientists have proposed even more exotic explanations for the cold spot. Could it be evidence of a collision with another universe, a glimpse into the multiverse? Or does it hint at a flaw in our understanding of inflation, the rapid expansion that occurred just moments after the Big Bang? These ideas remain speculative, but they highlight just how little we know about the true nature of the universe's large-scale structure. The cold spot isn't just a scientific curiosity, it's a window into the universe's deepest mysteries. Its existence challenges our assumptions, forcing us to rethink the rules that govern the cosmos. As we continue to explore these vast, empty regions, we're reminded that the universe is full of surprises, from the tiniest particles to the largest structures. Reflecting on the cold spot and the other anomalies we've explored, it's clear that the cosmos is far stranger and more complex than we ever imagined. Each mystery invites us to look deeper, to question what we think we know, and to embrace the unknown. The universe doesn't just reveal its secrets, it challenges us to discover them. And as we stand on the edge of the unknown, we're reminded that the journey of exploration is just as important as the answers we seek. From dark matter's invisible grip to the fleeting whispers of fast radio bursts, from the eerie emptiness of cosmic voids to the enigmatic glow of distant quasars, the universe is a place of wonder, mystery, and endless possibility. Each anomaly we uncover is a reminder that there's so much more to learn, so many questions still waiting to be answered. And as we continue to explore, we're not just uncovering the secrets of the cosmos, we're uncovering the story of ourselves, our place in the universe, and the boundless curiosity that drives us ever forward. So, as we close this journey through the cosmos, remember, the universe is vast and its mysteries are endless, and that's what makes it so beautiful. As we reach the end of this cosmic journey, let's take a moment to reflect on the 22 anomalies we've explored, each one a reminder of how much the universe still has to teach us. From the invisible grip of dark matter to the fleeting whispers of fast radio bursts, from the eerie emptiness of the Boötes void to the enigmatic glow of distant quasars, these mysteries have challenged our understanding of the cosmos in profound and unexpected ways. They've shown us that even in an age of advanced telescopes and groundbreaking discoveries, the universe remains a place of endless wonder and surprise. These anomalies aren't just scientific curiosities, they're windows into the fundamental forces and processes that shape everything we see. They push us to rethink our assumptions, to question the limits of our knowledge, and to imagine possibilities beyond what we currently understand. Whether it's the strange behavior of Tabby Star, the haunting silence of the Fermi Paradox, or the puzzling alignment of the axis of evil, each mystery invites us to look deeper, to explore further, and to embrace the unknown. But why does this matter? Why should we care about these cosmic puzzles? The answer lies in the very nature of science itself. Every anomaly, every unanswered question is an opportunity to learn, to uncover new truths about the universe and our place within it. Solving these mysteries could lead to breakthroughs in our understanding of gravity, particle physics, and even the origins of life. They remind us that the universe is far more complex and interconnected than we ever imagined, and that there's always more to discover. As we continue to explore these cosmic enigmas, we're not just advancing science, we're also tapping into something deeply human, our innate curiosity, our desire to understand the world around us, and our sense of wonder at the vastness of the cosmos. These anomalies remind us that the universe is a place of beauty, mystery, and endless possibility. To close, let's turn to the words of Carl Sagan, who once said, "Somewhere, something incredible is waiting to be known." These cosmic anomalies are that something incredible. They're a testament to the boundless creativity of the universe and the limitless potential of human curiosity. Now it's your turn. What did you think of these cosmic mysteries? Which one captivated you the most? Share your thoughts in the comments below. We'd love to hear your perspective. And if you enjoyed this journey through the cosmos, don't forget to subscribe and hit the notification bell so you never miss an exploration into the wonders of the universe. Thanks for joining us, and remember, the cosmos is vast, the questions are many, and the journey is just beginning.